Hello students, we are into the third lecture of the series of lectures designed by the University Grants Commission. I hope you are enjoying the mathematics, you are enjoying the partial differential calculus, and at the same time we have been able to follow the last two lectures on the base of which we will be covering now the third lecture. We will start basically with what we did in lecture 2, and then we will move to a very important thing called as chain rule and total differential. Most important examples that I will be taking, and it will be giving you an enjoyment of learning the partial differentiation to the greater extent. I will note down a few things by which you will be recalling the last two lectures. What we have done until now is starting with u is equal to a function of xy, then we had the du upon dx, then we had du upon dy, and then lastly in the lecture 2 we have done dx dy and d2 partial dy dx. Prior this we have also done d2u dx square and d2u dy square. Remember, these two are called as second order partial derivative, and this, as you know, is called as first order. This is called as first order partial derivatives. This we have done during the last two lectures. As I have told you, we will undertake a very important exercise by which the whole of the partial differentiation will be revised. So what we have now is to solve the second order differential, and that the example that I am taking is like this. One of the important example in the sense that it explains to you the whole thing of partial differentiation is given as if u is a function written as f of y plus ax plus we have phi of y minus ax. You are to prove that the second order d2u dx square is equal to minus times a square d2u upon dy square. As I have told you, this particular question or this particular example will make me convenient to understand the two things, and the two things are that how we differentiate for the second and for the other parts of the differential calculus. We solve it, and let me mark this as equation 1. No need to write anything because what you have done is known to you, and we will be starting with differentiating one time partially with respect to x, second time partially with respect to y, and then we will double differentiate it. It's like this. We proceed from 1. So number 1 implies partial du dx keeping y constant. Remember, we will be doing a theoretical function, is not a function like log x or x square or y square. So what we do is now this is written as f dash y plus ax, and then I'll be differentiating with respect to x the variable that is y plus ax. The second step or the second term, we will be having it as phi dash the prime that is y minus ax, and I'll be differentiating with respect to x. This will be y minus ax. I hope you have got it. F dash means the whole function is differentiated. Phi dash indicates the whole function phi is differentiated, and now we will be differentiating this y minus ax and y plus ax that we did even in lecture 1 and 2 as well. So I'll be continuing the right hand side as this. I'll be writing f dash, no change in it, y plus ax. Look into the second term. doing with respect to x, keeping y constant. So this will become 0, and we will be having only a from the first term. Second, phi dash will remain phi dash without any change, and then with respect to x again, y becomes 0, we will have it as minus a. So we have the first part of it, du dx keeping y constant is equal to a into f dash y plus ax minus times a phi dash y minus ax. Let me call it as equation 2, because after this I will be proceeding further to make it possible that we will be going with respect to y also. So we come to the next part of it, and similar, almost in the similar fashion, we will be having from equation 1. Again, this time I am doing with respect to y keeping x constant. So we will be having partial with respect to y keeping x constant is equal to, the function will be differentiated similarly, f dash y plus ax. This will be doing with respect to y, we will have it as y plus ax. This is the first term. I hope you have been able to make a very pinpoint about it. The second term now, phi becomes here, look from 1, becomes phi dash, the first derivative, y minus ax, we are taking with respect to y, and so it goes as y minus ax. In the same way as I have done here, the right hand side will continue, and I will be having f dash y plus ax. From here, note, I am doing with respect to y partially keeping x constant. So this term, as you look here, will vanish, will become 0. Y with respect to y, I recall we have done this thing yesterday also in lecture 2, and so it will be done as only 1, the second term, plus phi dash, this will give you y minus ax, and similarly this will be 1, this will give you, as I have told you, equal to 0, a is a constant, x is a constant, y is the variable, will give you 1. And so finally we will have here partial with respect to y keeping x constant. I will be having right hand side as f dash y plus ax plus phi dash y minus ax. I will keep it in a box to draw your attention that we have done this. I will be calling it equation 3, and similarly let me also make it inside the box so that you can make a difference of here equation 1 and this equation, equation 2 and 3. We go back now. Remember, we have to find the second derivative, because the result says that you will be differentiating the second derivative and you will be differentiating the second derivative also. So you will be finding d2u upon dy square, and you will be taking d2y upon dx square. So equation number 2 is required to be once more differentiated with respect to x keeping y constant. Similarly, if we look at this particular juncture, we will be having with respect to y again keeping x constant. So let me begin with equation 2, and number 2 implies we will be having it as, I am doing d dx again, du upon dx. We understand because of the last 2 lectures this can be written as d2u upon dx square. Of course, y is treated constant. On the right hand side, if you look from here, that is equation number 2, we will be having a, this will become double prime double dash y plus ax. Once again d dx, I will be doing y plus ax as we did in reaching 2, and then I will be having here minus a Double prime means second differential, y minus ax, and I'll be doing with respect to x, and so I'll be having y minus ax. That is the result that we have. We proceed further. Proceeding further thereby, this equation 2 can be rubbed out now. You have within your knowledge that how we have obtained. I'll be going from equation this one as I have left here. So therefore, I'll be having d2u dx square. Needless to say, y is to be treated as a constant. If you look here, I'll be having now y is 0 because that is a constant. Ax will give you a, x with respect to x will become 1, and so I'll be having it a into f double dash y plus ax, and this will become, and then minus times I'll have a, this is double prime, this will be y minus ax because it is a theoretical function, and here I'll be having minus a as usual. So we will be having a square f double dash y plus ax minus, this will also become turning into plus a square phi double dash y minus ax. This plus is because of these two negative terms. We make it plus a square. I take a square common, and we have inside the bracket f double prime means second derivative plus ax plus this will give you phi double dash y minus ax. Let me call it as equation number 4. And once again, I'll enclose it because that will give me the result. We now start from equation 3. So similarly, exactly similar. I hope now we can go little directly. Avoiding some steps here as we did reaching equation 4. So from 3, I'll be having d2y dy square. I am differentiating with respect to y partially, of course. X is to be treated as a constant. This is equal to, I'll be having f dash y plus ax, rather it will become double prime, and since we are doing with respect to y, once again we will have 1. This will be phi double dash y minus ax, we are doing with respect to, so it will be again 1, and finally I'll be having d2y dy square. X is to be treated as a constant, and we will be having here as f double dash y plus ax plus phi double dash y minus ax. Let me enclose it again because this will be the finishing part of our calculation. I will call it equation 5. Note here, the result is proved. The result is proved in the sense now that because of the equation 4 and 5, we will be having the result that if you have noted it down, d2u upon dx square is minus a square. So that is obvious. This is d2u upon dx square is this, and we have a minus sign taken here. So we note that the required result is proved. That is the first part of it. As I was mentioning you, a very, very important result, and we have been able to follow as to what we mean by these differentiation type of functions. We will be taking another example before we switch over to the main thing, that is of this lecture number 3, that is called as total differential and the chain rule. But I intend to take this exercise because this will help you in understanding the whole of the partial differentiation more clearly, and will draw before you a picture by which you can solve any problem at any point of time. We have this question, and while I solve it, of course, I'll try to make everything possible. The solution will be treated as simple as that, but you will have to understand as what we are doing and how many times substitutions that we are making. This exercise which I am taking. So this is example, the second example that we are taking for today. This is taken as, the example is, if u is a function of r where x is equal to r cos theta, y is equal to r sin theta, then you are to prove that d2u dx square plus d2u dy square, and then we will be having equal to f double dash r plus 1 upon r, this will be f dash r. We will making the solve. In order to prove this particular example, I'll be explaining you later some of the notations that have been used, not at the beginning. We will first solve this question as simple as mathematics. You will observe that here we have r, here we have theta. Theta is an angle. I hope we know about it. And then the second derivative is to be related. I will number them first. For example, I'll call this at equation 1, I'll make it equation 2, I'll make it equation 3. So first I'll make it number 2 and 3 implies, what we do is we square and add, we get this result, r square cos square theta plus r square sin square theta is equal to x square plus y square. I'll write it as r square into sin square theta plus cos square theta is equal to x square plus y square. We know from trigonometry that sin square theta plus cos square theta is equal to 1, and if this is 1, then this particular relation from here I can directly get that x square plus y square is equal to r square. Let me call it equation number 4. A very important relation to start with. I'll differentiate this, implies partially with respect to x. Remember r, this one, as I have told you, if you look into this particular relation, we will be having the given u is equal to fr, and so we will be having that this will be written as with respect to r, so it will become 2r, r as function of x. This is the important, r as function of x. So number 4 implies this will become 2x, y will become 0. For your convenience, I'll write it. This r square becomes 2 times r as a function, so dr upon dx implies dr partial over dx is equal to 2x. Let me call it equation 5. While I am solving, Please keep note of every step which I am making it a possible solution for it, so that we can make every steps much more clear. Similarly, I'll go back to equation number 4 again. So we will write also number 4 implies. I'll be having, this times it will be 2y, x will become 0, and this will become 2 times r dr. We are doing with respect to y. Implies that, to make a little correction, this 2 will cancel, and we will make it dr dx from here. This 2 will go away, and we will have x upon r. This x, r will be cross multiplied, so dr dx x upon r. Similarly, dr upon dy will be given as y upon r. I'll be calling it as 6th equation. As simple as that. And now, what we intend to, if you look into the proof, what we have said is proving d2u upon dx square. So we will start with the given relation number 1. Now, from 1, what we have is du dx. Look into the given problem. Into the given problem means what we have is given as u is a function of fr, and so we will be having it as f dash r into dr dx. This dr dx is because of this, keeping of course y constant, but since there is no y here, so we will be having f dash r. Look here, dr dx is given by x upon r. Dr dx is given by x upon r. We leave it here, and we come now to the same. Remember, we will be doing the second derivative. I continue from here, and I'll call it equation 7. We will be doing it like this. Therefore, the du dx will be equal to, I'm making a little change here, rearrangement, upon r into x. R quantities are taken into one side, x is taken as. Or I am doing second differential, so d dx, du dx, and this will become d dx of this whole function, that is f dash r upon r into x. This is what we get. With respect to x, and the result is obtained this way. The similar that we will be having, because in the result what we need is given this particular thing. We will be doing it as, I am considering this as first function, I am considering this as second function, and I am using the product rule. So this will be equal to, this will be equal to first function, that is f dash r upon r into differential of second, that will give you x, plus second function mean x, differential d dx of, this is f dash r upon r. A very important place where we have arrived. Before I proceed further, I will write it completely. d2u upon dx square is equal to, this will be f dash r upon r plus x. You cannot differentiate the whole thing r with respect to x, and r is neither a constant, so we'll have to make a little manipulation. This is how we do. Look at this step, the most important, that is why I was indicating that this is an example which will give you a whole idea of partial derivative. Please note how we manipulate here. this r with this r will go cancel, and d dx cancel means it is not a cross multiplication, but nonetheless we will be having d dx again what is written here. So this is what I will prefer you to note, and we will mark this equation as 8, and so I'll be having this d2u upon dx square is equal to, I'm doing with respect to x second time, and so this will be f dash r upon r the first term, plus we will be having x. I'm repeating this to evaporate any kind of this will be ddr, and then we will be having f dash r upon r, and the whole thing here is dr upon dx. I repeat, so this will be equal to f dash r upon r plus x. The quotient rule, denominator r, differential of numerator, that will give you f dash r minus the numerator, that is f dash r, into 1 upon r square. This dr dx will remain as such, and I'll be having now as f dash r upon r plus x. This will give you r f double dash r minus f dash r upon r square. Recall, I am substituting here dr dx which we have, and that is x upon r. This is all that from equation 1, 2, 3, 4 and 5. That is what we had. So I have reached to equation 9, and furthermore that we will be doing in our next lecture of this series, that is lecture 4. But before we close, I will tell you that we will have to find again d2u upon dy square in almost the same fashion, in almost the similar calculation, and we will try then to add these two results, and we will be using this also, x square plus y square is equal to r square, because if you note that what we want to prove, it does not contain any kind of x or y variable. The result is given simply, as you can see on the right hand side, is only r. So we will have to replace whenever x square plus y square comes with r square, and that will make possible for us to arrive at the result. But that we will be having in our next lecture, meaning thereby when we meet in the lecture 4 of this series. But until then, try to get your expectation and your efforts to complete this example with its solution. Thank you.